Dear fellow scholars, thank you so much for coming today. I got to hold on to my papers for this one. So, I got an interesting message a few weeks ago. Someone asked, Károly, we have 4 legendary scientists, and we want to make a roundtable discussion for them. Do you know anyone who could hang with them? And I said, no, nobody can. Now, before they drag me off the stage, I'll get to learn from them about their incredible works and how they will enhance our lives. Don't forget that a lot of what you will hear today is technology that is free for all of us, forever, which is absolutely amazing. And I have some questions for them to reveal how all their works are connected to build a better world for us. Now, don't worry, I won't be long. Let's see. Oh, yes. This is a good one. This is a good one. All right. Kidding. So first, she is a senior director of AI research and professor at Stanford and University of Washington. She won 4 prestigious Best Paper Awards just last year. Please give her a big hand. This is Professor Yejin Choi.
All right, we have a situation. NVIDIA GPUs are getting ever faster and better, but you guys are not posting social media fast enough to keep up with the data demand. So Ilya Sutskever said at his Test Time Award talk less than 2 years ago that this is a situation. I'm excited to share what we're doing at NVIDIA Research in order to cope with that data shortage. But let's look at how LLM sausages are made, just to motivate what we do. So it starts with the pre-training on the entirety of internet data, followed by sequential fine-tuning on lots of curated exam-style data. Those two together is a form of imitation learning. You only imitate what's in the data. But we now all heard about RLVR, or reinforcement learning with human feedback, which allows the model to explore for itself instead of just doing imitation. So that really opens a new era where the model begins to learn to explore. However, there are 2 questions. One is, exploration only comes at the very end of this pipeline. And is it just how it always should be? And can we somehow inject this reasoning earlier to the pipeline? So what we propose to do is RLP, or reinforcement learning as pre-training learning objective, where we start with this context, and then usually during pre-training, you just predict the next token. But instead, what we do with RLP is that we let the model to think for itself, even during pre-training, before predicting the next token. So when we do this, the results were super surprising and exciting. We were measuring this before and after, post-training. We were measuring this by controlling the amount of compute, etc. All around, it's looking very exciting. So the future will be really the era of explorative learning, and we are very excited to push that through. Thank you.
All right, next up, we have Director of Autonomous Vehicle Research. He's working on making software for self-driving cars a reality and giving it to all of us for free. He also won the Presidential Early Career Award by President Obama. So next up, please welcome Professor Marco Pavone.
Oops. Thank you. So a core area of research for my group entails the development of reasoning models for autonomous driving, an area where we've been actively contributing to and sharing our work with the community. As you may know, at the latest CES, NVIDIA unveiled the Alpamayo Open Platform, which is an open ecosystem of AI models, simulation tools, and a data set to accelerate the development of reasoning-based autonomous driving solutions. The Alpamayo platform entails the Alpamayo 1 model, which is a 10 billion parameter chain of thought reasoning visual language action model built on the Cosmos Reason Visual Language Foundation model. AlpaSim, which is an end-to-end simulation framework to test end-to-end AV stacks, and the Physical AI AV dataset, which is one of the largest and most geographically diverse dataset available. And everything is open. Models, code, datasets, everything is available on Hugging Face and on GitHub. And let me give you a glimpse into the Alpamayo 1 reasoning model, its core principles, and associated development tools.
The next frontier of autonomous driving is enabled by the power to reason. This means developing models that can think through extremely rare or never-before-seen situations and act accordingly. NVIDIA Alpamayo is helping make this happen today with an ecosystem of open components that brings together AI models with reasoning capabilities to make decisions, closed-loop simulation tools to test those decisions, and massive real-world driving datasets to learn from. Alpamayo 1, the first release in this family, is a large vision language action model that integrates visual perception, language understanding, and action generation with reasoning to explain its own decisions. Alpamayo 1 can more accurately perceive the environment, interpret context, and anticipate risks through reasoning. These explicit reasoning traces ensure logical consistency and trustworthy explainability.
So since its release, the Alpamayo platform has seen an incredible adoption by customers, OEMs. And this week at the GTC, we are announcing a number of extensions and upgrades to the Alpamayo platform. First of all, the release of Alpamayo 1.5, still a 10 billion parameter model, but now offering navigation and text prompt guidance, making it much more flexibly steerable. We're also releasing, based on customer demand, post-training scripts, for example, supervised fine-tuning scripts and post-training alignment scripts to allow developers to customize the model to their own datasets. We are expanding the scenes that you can test your AV stack against within AlpaSim, and we are releasing our reasoning labels and the chain of thought auto-labeling pipeline to lay the foundation to further the research in this field. To learn more, please, I refer you to the Hugging Face blog post that I released yesterday. Please note that the links will become, all the links will become active by the end of this week. Thank you.
All right, our next guest is VP of AI Research and head of the Toronto AI Lab. She is a master of simulation research. She has a bunch of Professor of the Year and Best Paper awards and more faculty awards than I thought ever existed. So please give it up to Professor Sanja Fidler. Woo!
All right, hi everyone, and thanks, Károly. All right, so Mark already touched upon some key elements of AV development, and here we're going to focus on simulation, which is really a critical tool to test the AV software before it hits the road. So traditionally, this was based on graphics, right? It was basically like graphics-based game engine for robots. Now, the key limitation of that was that it relied on human-authored content, and you just can't author the entire world, right? So it was not scalable. Now, neural reconstruction, like 3D Gaussian splats, really changed the game. So now you could go from a real recording, reconstruct it, and get like a simulation environment to get new experiences for the policy. And I'm just going to play a video here.
As vehicles, real-world data is transformed into Gaussian-based 3D scenes using omniverse neural reconstruction, or NUREC, converting video into photorealistic digital environments. The reconstructed scenes are then simulated with variations to assess the AI driver's ability to generate safe trajectories. Physical AI isn't just driving on roads, it's operating in kitchens, offices, and warehouses. Each of these robots needs to be simulated in virtual worlds reconstructed from multiple sensors. With NUREC, we can rapidly render these simulations in real time with high fidelity. New capabilities like physics bring realistic interaction to 3D Gaussian scenes, letting robots engage naturally with virtual environments. Generative AI uses the visual properties in these simulations to add diversity, scaling a single scene into many. Neural reconstruction is already advancing the world's physical AI. And now, with just a text prompt, NUREC and Cosmos can generate 3D simulation environments that refine testing and validation for the next generation of robotics.
So super proud this stack was actually integrated in the internal production stack for simulation. It's running 2 million tests per day, so it's really providing value to the AV development. So the question is, what's next? Black screen is next. Yeah, so we enter the era of generative simulation, right? And the whole idea here is that you're training a world model on massive amount of visual data to basically learn how to simulate. It's purely bound by data. And this approach can basically generate completely novel scenarios, really challenging things to simulate, for example, like rain, snow, or a mattress on top of a car. So last GTC, NVIDIA announced Cosmos. There's Mingyu somewhere in the audience, thanks to him. And it was kind of the first generative simulation of its kind. However, at the time, it basically took several minutes to generate just a few seconds of video. And today, we're announcing Alpha Dreams, which is real-time, interactive. And the first user to test this is our first employee of NVIDIA, our favorite NVIDIAN, Jensen. So Alpha Dreams essentially simulates multiple cameras, all real time, in reaction to the policy. So they're basically like running in closed loop. And it's also super easy to edit the scene. So you can change the weather, add objects to the scene, and really test the policy in different conditions. We have a demo at the booth, so after this, I'm going to head over there, so please join me. You can actually steer and drive in this generated world. So thanks.
How cool is that? And finally, he is leading the simulation and behavior generation team. He simulated 1,000 simultaneous nut and bolt interactions in real time on a single GPU. Please welcome Dr. Yashraj Narang.
All right, let's talk about robotics research. I'm going to take you on a small journey with a heavy focus on simulation and sim-to-real. So I had a feeling Károly would introduce me in that way. So this is 1,024 nuts and bolts being simulated in real time on a single GPU. Every single contact is actually being simulated here. We followed up this line of work by introducing robots into the scene. This is actually a vibratory feeder mechanism that's vibrating at 60 hertz, although you can't see it. These hex nuts are being channeled. The robot is grasping one of those hex nuts, and it's placing it onto the bolt. And we can do hundreds to thousands of these environments in parallel in real time. Because we can do this so fast and so accurately, we can actually use it for reinforcement learning training, leveraging algorithms that are very sample inefficient, but very, very powerful, like PPO. But we didn't just do this in simulation. We actually brought this to the real world. So here we are assembling gears with policies that were learned purely in simulation, again and again and again. We didn't just do this for gears. We can actually even bring this to multi-part assemblies. And we can do this in the dark. So this is actually simulating tactile sensing. And this policy was deployed in the real world, and we can actually assemble parts without any visual feedback. Now, we really wanted to push the boundaries of simulation. We wanted to go beyond classical simulators. We wanted to move into the world of neural simulators. And this is us generating data for a neural simulator just by applying random actions to robots. Ultimately, we trained a neural network on this data. And then we learned policies in that learned simulator, which we call neural robot dynamics, or NERDs. So here is forward walking, and here is sideways walking, learned purely in that neural model. And then we brought all of these learnings together and focused our attention inwards on the hardest problems that we knew of, NVIDIA's own problems in assembling its GB300 superchips. We're able to perform 20-part assembly procedures in a very reliable manner, meeting industrial standards. We don't just manage rigid bodies, we can even insert cables into very tight clearance connections, and we can do so again and again and again. And this was pre-trained in simulation, followed up by a real-world learning phase using reinforcement learning. And finally, we don't just handle rigid parts or tight clearances, we can even control the configuration of deformable objects. So this is zero-shot sim-to-rail transfer from policies that were learned to manipulate cables and route them through harnesses in a way that's agnostic to the cable that's used. Where do we go next? We're focusing more than ever on industrial assembly and trying to accomplish the rest of the challenges in NVIDIA's own compute assembly problems. We're also driving towards scientific lab automation. We'd like to build automated and autonomous robot scientists. And finally, we're going into the homes. We're focusing on unstructured settings, and we want to handle the messiness and unpredictability of the real world. Thank you.
Woo. Amazing. We are going to follow up with some questions, and then we are going to play a game. You'll never guess what it is. All right, Yejin, is continual learning of models the future?
Yes, so I told you about RLP, which is a form of explorative learning during pre-training, but we can definitely expand that spirit even for the deployment time during test time by bringing training into the deployment time. So that I envision will be one way to really push the frontiers of AI by allowing the AI model to mix the, what happens during training and what happens during testing. And in spirit, it's analogous to what I presented today, which is to mix some of the stages of a training between the pre-training portion and then the reinforcement learning with the human feedback portion. And then going forward, I envision we will see even more hybridization of different stages of AI training and deployment.
Mm-hmm. Marco, you mentioned that AlphaMayo is using a reasoning model. What does that mean and how does that help?
Yeah, that's a great question. So at a high level, reasoning can be viewed as the process of taking a complex problem and decomposing it into smaller, more manageable problems, and then plan an action step by step, going through this decomposition. But now we have conclusive evidence that forcing the model to carry out this process leads to better actions, more performant actions. It gives you an introspection signal. It gives you a glimpse into what the model is thinking before planning an action. And also, it provides a signal that can be used for safety purposes to understand, for example, whether the model is certain about what it's doing or not. So it's a technology that achieves multiple purposes, and we're advancing it along multiple fronts.
Mm-hmm. When I read this AlphaMayo paper, I felt like previous systems that are non-reasoning, self-driving systems, I'm feeling like it's a bit like sitting next to a teenager who's driving. Smashes the gas pedal, and you're like, whoa, why did you do that? And it says, I don't know, hormones, something.
We're not there yet.
Yeah, yeah, and this actually reasons. But then I found out that it's not like you just say to the AI model, reason. Because you had this problem during the research that it says things, and then it does things. And it says that if there's going to be a red light, I'm going to stop. And then there is a red light, and it is like, whew, just goes through. So you needed to do something, this reasoning action consistency step to fix this. Can you tell me a bit about that?
Yeah, so essentially the model is producing multiple output modalities. It's producing reasoning traces, so explanations in plain English about what the model would like to do. And it produces actions, so trajectories in the physical space. And we want to make sure that reasoning and action generation are reflective of each other. For example, I like to make an analogy whereby I like playing tennis, but I'm not a particularly good tennis player. And sometimes my brain has a very sophisticated strategy about where I want to throw my ball, but my body does something completely different. So that's embodiment misalignment. So we want to make sure that the reasoning and action generation are reflective of each other, so that action generation fully harnesses the power of reasoning, but at the same time, reasoning faithfully represents the action being generated so that it can be used, for example, as a safety signal. To do so, we introduce an additional training step, which is referred to as post-training alignment, whereby we build an explicit coupling between the two output modalities that brings these two output modalities together so that, again, they are very reflective of each other. And we've seen through extensive experimentation that this effectively allows the model to produce reasoning traces that are very faithful. At the same time, it gives you actions that are even more performant.
All right, Sanja, are world models the way to go?
Yeah, great question. So I've been at NVIDIA for 7 years, a long time. So I've seen actually an evolution of these simulation engines throughout the year. And you can definitely see the upper bound of every type of simulation. So for example, when I joined, they were using these graphics engines. And if you wanted to test the AV software in, let's say, a new intersection in San Francisco, then you would wait 1 or 2 months such that the artist would actually create it, and then you can go and test it, right? So clearly, there was a very low ceiling for that approach to kind of make an impact. And then as soon as neural radiance field came out, that was basically 2020, basically the next day we decided, okay, that's the next step that we need to do. So you could actually just take a real-world recording and convert it into a simulation environment. Now, obviously, even with this approach, which was totally pragmatic at the time, you can still see a lot of limitations, right? So for example, imagine in the original recording, the car stops a few meters away from a pedestrian, right? And the pedestrian just kind of walks across the street. If the policy later in simulation stops 10 centimeters away from the pedestrian, the pedestrian is going to look really different, right? They might run, they might flip a finger, whatever, right? So it's going to look very different than in the original recording. And that's just kind of not possible with that type of approach. So world models basically just learn how to simulate from data. So as soon as you have seen such situations in the real world, which you do, then that's basically the ceiling, right? And we've seen with LLMs that the data-driven approach can really move mountains, right? So definitely think it's going to be the future. Maybe not as designed today, right? We need to simulate a lot more than just cameras. There's so many sensors on robots, also generate forces and so on. So there's, it really feels like the real world, but definitely this kind of learning-based approach is the simulation engine of the future.
And just to emphasize how remarkable that we have world models, I gotta say that you used to write these handcrafted simulations where you program every single grandma on the street, every single traffic light, every single whatever is one paper. And now we have just one model that does everything, which is, I think, absolutely amazing. Now, Yash, how does NERD, Neural Robot Dynamics, I'm not calling you nerd, just how does NERD teach robots complex physics, and how is it possible that they learn in their own imagination?
Yeah, and this is a great question. First of all, Károly, thank you for featuring NERD. I think it was your 1000th episode. I think I've even seen your first episode, so I've been there for the whole journey. It was an honor. So how does NERD actually learn? What we do is, as I briefly mentioned in that video, we take robot models in ground truth simulators, we apply random actions to these robot models, and we generate a very, very diverse data set. We then train networks to learn from these data sets. And of course, we have a few different strategies to doing that very effectively. One of the key strategies is to represent the physics of the world in a robot-centric frame. So of course, the physics when I stand here is the same as the physics when I stand over there. And so that's one of the key tricks to actually make these predictions generalized. There are a number of other tricks and tools on the learning side, using the right network architecture, doing the right normalizations, really collecting the right data and sampling the right data during training. But that's really the essence of it. It's really getting a diverse data set, training a network on that data, And then in terms of actually using it for policy learning, we use it just like any other simulator. So what's really nice is that this neural network basically takes in the same simulation inputs that a classical simulator does. So it takes in your robot state, it takes in joint torques, it takes in contact information, and it can predict next state. So from the simulator's perspective, it acts like any other solver. And you can just treat it that way, and you can learn policies in imagination.
Mm-hmm. All right, let's play a game. You'll never guess what it's going to be. OK, so something really cool is going to happen. I call it, hold on to your papers. I will show you papers, and I'm hoping that the panelists can guess what it is. Now, if you know it, please don't say it. But if you know the answer, just raise your hand so I can see that. OK, let's start with something easy. Easy, easy, easy. Raise your hand if you know what this is. Come on, hands, hands. OK, some fellow scholars here. All right, who knows this one? Anyone?
It's cute.
It's cute. OK, so which paper is this?
Transformers.
Transformer. Excellent. Very good. After the warm-up round, who knows what this is? I want to see some hands. Very, very good. Excellent. Some hands. OK. Any tips for this?
There's a hand over there, man.
OK, who was? Yeah. There we go. Nerves. Nerves. There we go. Excellent. Come see me after the talk. You're going to get the badge of honor. Hands, hands. OK, OK, nice. Who knows what this one is?
Oh, that's obvious.
OK, yes?
Can I say it?
Yep.
Alpha Mayo.
Yeah, there we go. There we go. OK, I got a couple more. I wasn't sure if anyone is going to guess this, but let's try. Anyone knows what this is? A couple years back. I'll give you a hint. OK? This is a flaming O. Does it ring a bell? Yep, gentlemen? Yeah, this is flamingo. There we go. Good job. Good job. OK, I got one for a very specific person. This is for a very specific person. This is for a very specific person.
3D.
Say it.
I know.
Say it.
3D brain?
3D gut.
3D gut. There we go.
Oh, God.
OK, can you...
We made a joke last year. Nice.
Can you explain them, please?
Thank you, Karoly.
Can you explain them briefly what this is?
Huh?
Can you explain this, what this is?
Yeah, so it's a name of a method last year. We had a new method that does reconstruction that also models like secondary lighting effects. So that's ray tracing, essentially, and we named it 3D gut. So everyone was making fun of me on stage, and I guess it's going to also be this year. Thank you, Karoly.
So they called it 3D GUT, and I was like, come on, man, that's 3D gut. It's gotta be. It's gotta be.
Have you featured all of those papers on the channel?
I have a last one. This is for the real fellow scholars. This is for the audience. Does anyone know what paper this is? Anyone? Oh, my. Oh, my. OK, I'm going to tell you this one. This is called wavelet turbulence. And this is one of the best papers ever written. Won an Oscar award. All right. Yejin.
Yep.
How do synthetic data sets help training today's AI models? And can they measurably help iron out their blind spots, things they don't do so well on?
Oh, yeah. I mean, like, synthetic data is used so much these days, especially in order to overcome the data shortage. Internet data not only is not growing fast enough, but also it doesn't really cover all the corner, long tail situations that our AI should cover. So In order to overcome that, sometimes we pay human workers in order to curate data. But these days, it's really powerful to just rely on AI to synthesize a lot of data. And by the way, one overarching theme from this panel so far has been reasoning, right? Reasoning, what is reasoning is that it needs to connect the dots across different pieces of knowledge, and oftentimes it should do that for the first time. And so in that sense, whenever the model is generating reasoning traces that's genuine for the brand new reasoning trace that was never there before, we're essentially synthesizing new reasoning tokens. And then that can then be used in order to strengthen the AI models even further up.
Marco, what's next in this space?
Well, particularly in the space of reasoning models, I think we're still scratching the surface of what is possible. For example, in the video that I showed before, I showed the reasoning traces in the form of textual reasoning traces, so explained in plain English. But as humans, we reason with different modalities. We reason in terms of visual concept. We reason in terms of more latent representation. So I think a very active area of research is how we go beyond the textual representation of reasoning into other modalities. And I don't see all these modalities in contradiction with each other, but rather how we can synergize all of these modalities to get a system that is more performant and also more efficient from an inference standpoint. Or how we use reasoning. For example, one of the power of reasoning from my point of view is to plan in semantic spaces in a counterfactual way, trying to understand what might happen under different assumptions, basically asking what if type of questions that we as humans, we ask all the time, and it's very important to empower machines to do so as well. Again, how to do this in a very performant way, in a very efficient way, is still very open. And I could continue for half an hour listing all the research questions that are available in this area that, as I said, I think is extremely active.
Amazing. Sanja, do humanoids need a different simulation environment than self-driving cars? Can you have one unified environment that is good for both?
Yeah, I'm tempted to say that we need one simulation model in the future. And the reason is that we're going to have multiple robots in the same world, right? Maybe today they're still separated, a humanoid in the kitchen, a car on the road. But in the end, we're going to have multiple robots designed for different tasks and living in the same world. So it doesn't seem plausible that we would just have a simulator per robot because you need to simulate one coherent world for everyone. So I think the future is kind of clear. I think that's where we need to get to. It's kind of there today to some extent, but there's also differences. So for example, if you look at GRU Dreams, which was a simulator by Jim Fan just a few months ago released, and Alpha Dreams, they kind of share the same technology. This is this like autoregressive causal model based on Cosmos that generates frames based on action. And maybe the action is a bit differently represented, but kind of the core tech is the same. But then there's differences because a humanoid is all about interaction. You know, I need to go to the kitchen and touch a bunch of stuff, right? That's how the robot is learning. In AV, if you touch something, that's game over, right? So the type of interactions you need to simulate is very different. So robotics right now is much more heavily leveraging these physics-based simulators. That's kind of in the heart of it. And while AV is more just about visual fidelity, diversity, and really going after that kind of scale in the real world. But definitely in the future, I think we're kind of going to converge probably towards one engine for all robots.
Yash, what are the big unsolved problems in neurosimulation?
The big unsolved problems. I think the key one, so I'll just give you a concrete example. We've done this NERD framework, this NERD paper, and what we're looking at now is how do we actually extend this to model very high degree of freedom systems. Humanoids are a great example. So I think each of our human hands is around 27 degrees of freedom. We have 2 hands, we also have arms, we have legs. I mean, this could be an 80 degree of freedom plus system. And the way that we're currently generating data in these NERD models is through applying random actions, essentially, to the robot. And as you can imagine, if you have a 80 degree of freedom state space, actually a little bit greater than that, 80 degree of freedom action space, this doesn't scale well at all. You really need to do this in a more meaningful and a more intelligent way. I think this is a real opportunity for, especially those who are coming from the RL community, might be looking at things like intrinsic objectives, intrinsic motivations, things like diversity and curiosity and empowerment, to actually learn how to generate data that is in a meaningful way, that is in a really meaningful subspace of the gigantic space of possibilities of states and actions. So I think that's probably the #1 challenge. And the second challenge is that if you have a neural simulator that was perhaps trained on simulation data, pre-trained on simulation data, how do you actually fine-tune that on real-world data? Because in simulation, your inputs might be things like joint torques, and they might be things like contacts. Okay, in the real world, you might be able to get joint torques from your robot. Hopefully you can. But contacts, how do you do that? You need to perceive the world. You need to actually somehow extract contact information from the world. Or you need a strategy that is a robust enough training strategy that can actually not rely on that data and actually train on very, very heterogeneous mixtures of data, some from simulation and some from the real world. So I think that's where we need to take it next.
All right. If we can, I'd like to have some questions from you fellow scholars. Can we do that? Maggie? Okay, let's see if the situation improves, and I'm gonna.
There was one there.
Yeah, but I don't know if there's gonna be a microphone or not. Okay, just shout. That's fine too.
All right, I'll shout. Yejin, this is for you. I have so many questions about reinforcement learning with pre-training. I'll save it for later. Do you think it's going to be more along the lines of stuff that all happens in context, or do you think for continual learning in the future we're going to have to actually update the weights of the model? So in context or just updating weights? What do you think?
Yeah, I can repeat the question. So the question is, what happens with continual learning? Does it have to be just like putting everything in context, basically, making prompt engineering more informed by, whatever happens during inference time, or do we update the model weights? I think both are on the table. In fact, I have done research of both flavors, and the benefit of updating weights is that you get so much more focused specialization of the model, really zoning in for that one hard task that seemed so hard to solve. So we have a recent paper called the TTT Discover that performs lightweight RL on top of already trained model. And when you use OSS GPT, the open source model, it wasn't able to do certain kinds of a task well enough, but when we train the model to learn from its own past mistakes this is what happens during inference time, we were able to really push or unlock the capabilities, hidden capabilities that were kind of there, but the model wasn't able to perform before. So I think there's an amazing future in this direction to really explore different ways of doing model update during test time. But one thorny thing is that you cannot really update model weight for everyone all the time. So there's some decisions to be made about how exactly to do this right in practice.
All right, if someone promises me a super quick question and answer, who has a super quick? Okay.
What is the future of recursive self-improvement?
So I can take
Who wants
this
to
one
take
too.
this?
Yeah.
All right.
The future of self-improving AI. I think that is the future. I am very excited about the future of AI scientists, this AI that is really able to discover new knowledge for us. Current day AI, especially with LLMs, they tend to be more of an interpolation of known knowledge or composition of familiar pieces of knowledge, whereas we really want extrapolation above and beyond what human knowledge have found out. So in order to get there, we need a self-improving AI. I think there's a lot of potential coming from coding LLM agents and other kinds of agents. I think in the future also in the embodied space, we're going to see a lot more exciting results as well.
All right. What an amazing panel. Sorry, we have to go. Unfortunately, I want to stay for longer, but they're going to throw me out. So what an amazing panel. This was stunning. I mean the creators of some of the most amazing technologies of our lifetimes. What a time to be alive. All right, so thank you so much to all of you for coming.
Let's give it to Károly.
Thank you. Amazing.